Okay, let's take a look at our final optimization problem. Here they want you to design a 1-liter oil can that's shaped like a right circular cylinder, and they want to know what the dimensions will be that will use the least amount of material. So sometimes they attach a cost to this and they give you so many dollars per square centimeter or whatever, and you need to find the optimal cost. Here, note that 1 liter equals 1,000 cubic centimeters. So um, start off by drawing a cylinder. Alright, let me erase the middle part here. Okay, so something similar to that. Note that the volume of this is what? Pi r squared times h. And we know that this is equal to 1,000 cubic centimeters. Well, do they want us to maximize the volume? Or do they want us to maximize another formula? So let's see. We're trying to use the least amount of material, so we're not going to be dealing with volume, we're going to be dealing with surface area. So when we maximize the surface area, first we have to figure out what the surface area formula would be for this. Well, this surface area has a top and a bottom, right? And the top and the bottom are just circles. So those would be 2 times pi r squared. And then we have the wall, right? The circular part. If we cut the top and the bottom of the can out and stretch it out, we have something like this. So this right here is the height of it, and this is the circumference of the circle. So to find the area of this, it's 2 pi r times h. And since this is the one we're going to take the derivative of, we look at the equation and we notice that we have an r squared term here and an r here, but then we have this other variable h that we need to resolve before we take the derivative. So is there a way that we can rewrite h in terms of r? Well, it turns out there is. If you go back to this first equation for volume, if we solve in terms of h, what would that equal? H is equal to 1,000 over pi r squared. So all we need to do is two pi r, and then have it over 1,000 over pi r squared. Alright, so you can simplify this by dividing out a pi, and this radius takes this down to r to the first power. So our surface area is equal to 2 pi r squared plus 2,000 over r. Well, maybe it's easier if we write it r to the negative 1. So now let's take the derivative of this. So we have ds over dr, taking the derivative with respect to the radius, and we get what? 4 pi r minus 2,000, and this is r to the negative 1 minus 1, or minus 2. Well, we can just rewrite this over r squared positively. Okay. So now, what do we need to do? We need to set this equal to 0 and try to solve, right? So we can do it up here. We set this derivative right here equal to 0. We would have 4 pi r minus 2000 r squared equals 0. So if we move this over to the other side, we have to add it, correct? So if we add it, it's going to end up being positive. So now, if we cross multiply, we get what? 2000 equals 4 pi r times r squared gives me r cubed. And divide this by 4 pi. You get what? 500 over pi equals r to the third power. And so to solve this, we have to take the cube root of both sides. Take the cube root of this side. And that gives me that r is equal to what? Approximately, let's see, 5.42. Alright. So, let's see. So what are our dimensions of our can here? This is our radius, and this is our height. But we know that the height is also equal to what? 1000 over pi r squared. Okay. And if we were to do an analysis on this, 5.42, of course we'd have to use the calculator on this, but we can approximate it, right? Let's pick a value like 1 for the radius. Alright, let's switch colors, because 1 is definitely over here, right? So we have 4 times pi times 1 minus 2000 over 1. Well, this is just simply about 12, right? 12 take away 2000 is definitely approaching negative territory. So our function is decreasing here. And then let's pick a number well over to the right, say like 10. So plugging that in, we get 4 times pi times 10 minus 2000 over 10 squared over 100. That reduces to 20. So you have 4 times 10, we have 40 pi. Put it over here, we have 40 pi, which is about 120, 130 something. And then 20 minus 20, right? So this is clearly positive. So the function starts increasing again. So this tells me that I have a minimal amount there, right? Alright. So I guess the only thing left to do is to come up with a dimension. This is our radius, right? So I guess we have to come up with, substituting back in over here, we have 1000 times pi over 5.42 squared. And let's punch this up on the calculator and see what we get. We have 1000 divided by pi times 5.42 squared. 5.42 squared. that should give us a height of 10.83. So that tells us what our surface area is going to be, and gives us the dimensions for the radius and the height. Okay. Well, we might put up another optimization problem, but hopefully this gives you an idea of how to attack these problems.